Let's start again. For this afternoon session, we have the pleasure to have Renaud Guéroult, who is now a CNRS in Toulouse. He has been since 2015, and prior to that, spent 4 years in Princeton, working with NetFish, for those who know. So his collaborators are NetFish and Jean-Marcel. So, Renaud.
Thank you, Guillaume. Good afternoon, everyone. First, I'd like to thank the organizer for the invitation and the opportunity to present some of our work. It's a pleasure for me to be here today. What I'd like to do today with this presentation is to give you an overview of work we've been doing on the effect of motion and flows on plasma waves and reciprocally. And I'll get to what I mean by that more specifically in a minute. As you'll see, the interplay of plasma flows and plasma waves is something I'll be addressing here as a basic plasma physics problem, but we are aware and very much looking at the possible implications for that in various contexts, including astrophysics and magnetic confinement fusion. And so I'm hoping that this presentation can stimulate some discussions around those implications. So this is work that's basically at the moment supported by the National Research Agency in France, which as its core, as a couple of grad students and myself in Toulouse, that builds on a number of collaboration, including with NetFish in Princeton and Jean-Marcel in Paris on theoretical aspects, and also with the basic plasma physics team at UCLA regarding the experimental demonstration of some of these effects on the large plasma device. So let me first tell you in one slide why we're actually interested in looking at the effect of motion on plasma waves. So on the one hand, you have waves in plasma that are used for a variety of applications, including control and diagnostics. So that's what you've got on the top here. Here you have basically a cyclotron wave that's being used for plasma heating in tokamak. And at the bottom, you've got a wave that's generated from a distant source, from which you can infer properties of the interstellar galactic medium. And in this case, basically, you can use farther rotation to determine the interstellar galactic magnetic field, and you can get a full sky map of the galactic magnetic field for this system. What's interesting is that whether it's for the design of those control schemes or for the interpretation of the diagnostics, we typically rely on plasma wave theory that assumes that your plasma is static with respect both with the emitter or the source and the observer. The reason this is somewhat interesting is that we also know very well that most of our plasmas actually feature flows, in particular rotation. So that's what you've got here on the top with the rotation of tokamak and rotation of the accretion disk around a black hole. This is something that we know to be true at various scales in plasmas, from laboratory experiments all the way to astrophysics. And so the reason we thought that was actually interesting is that we also know now for a long time we've known that basically motion affects wave propagation, and that we know very well in isotropic dielectrics. So you can think here of Doppler and aberration effects, but I'll get to in a moment. There's much more to that than just these effects. And so the question we asked ourselves at the start of this project is, how is it that basically we don't consider, for the most part, the effect of motion on our waves in plasma? Is it supposed to affect our diagnostics or control schemes? And beyond that, is it something that we could actually use to our advantage? So here is the outline of my presentation for today. So to motivate further the investigation of this effect, and to tell you a bit more what motion can do to your waves, I'll start by reviewing what's been known now for a very long time in isotropic dielectrics. And this will also help us identify better what we could expect different in plasmas and what could be interesting. Then in the second part of this talk, and largest part of this talk, I'll focus on what we've learned in plasma. So for that, I'll begin by focusing on one particular configuration, which is a rotating plasma column. So in this particular setup, I'll discuss two different effects of rotation, one on the spin, that is on the polarization of your wave, and the other on the orbital angular momentum of the wave, discussing as I go possible application, and finally showing you what our first experimental evidence of these effects that we obtained in LAPD. Then to finish the second part, I'll discuss what we're currently doing to look at configurations beyond this idealized rotation of column, so as to get tools to basically assess the importance of these effects in realistic configurations. Finally, time permits, I'll tell you a few words about the reverse or the reciprocal problem, which is basically now how waves can drive flows, and I can drive in particular rotation, and what we could do and what we want to do with it. So first, let me just go over what's been known now for motion in isotropic media as a starter and as an introduction for later discussion of plasmas. So the idea that motion can affect wave propagation goes back to the first half of the 19th century in the work of Fresnel, Fizeau, and Stokes. And you have here on the upper right the experimental setup that was used by Fizeau to demonstrate these effects. So the idea behind Fizeau experiments is what's at the bottom here, basically to study the interference pattern of two beams that propagate in opposite direction in a water flow. So you have here a red beam that propagates along the water flow that basically is mixed with a blue beam that propagates up in opposite direction in that water flow. And what Fizeau observed is not only that the wave propagating along the water flow has an higher phase velocity than the wave propagating against the water flow, but the difference that he measured is precisely the one shown here, which is what was postulated theoretically by Fresnel some 25 years prior. So historically, it's very interesting because this result is based on the assumption of partial ether drag, which we know now is basically not true. But this formula is perfectly consistent with what you get from relativistic theory these days. And so that can be understood as a refractive index that's going to depend on the motion of your medium. So although Fresnel and Fizeau only consider the case of a longitudinal drag here, which is basically when you have a motion v here that's parallel to your wave vector, the case of a motion perpendicular to your wave vector was later studied. And in this case, what was shown is that it's no longer your phase velocity that's modified, that's your group velocity. And what it does is that basically it gives you a deflection of your beam. So you have a beam that's normally incident on that gliding medium here. And what you see is that basically the beam is shifted laterally in the direction of motion of your medium. So practically what this means is that if you have a receptor, you should not put it in the direction of the source, basically put it at this position, so laterally shifted vertically in this case, if you want to measure any signal. So this is an effect which is, because it has the same scaling as the original effect measured by Fresnel, this is called transverse Fresnel drag. So particular configuration and effect of transversal drag that I'll be getting to discuss today is the case of a rotation. So in this case, you basically have a wave vector that's now parallel to the rotation axis of a medium here. So probably see better out there, but you basically have a rotating cylinder here. And so from what I was describing so far, what you expect in this case is this sort of azimuthal shift of the beam. That's basically the rotational analog of this linear shift that you're observing here. So interestingly, this effect has only been observed somewhat recently in the form of what's known as image rotation, which is what's shown here. So what you have shown here in color scale is the transverse structure of the wave in the direction perpendicular to your primary wave vector. And what you see here is that that's the entire structure of the wave that's being rotated as you propagate from left to right along the direction of propagation of your wave. And so this basically can be understood as the coupling mechanism between the wave's orbital angular momentum and the rotation of your medium. And you can think of it as basically any point of the structure here to be dragged azimuthally as the blue array that's drawn here. So that's one effect of rotation, but it's not the only effect of rotation. Turns out that this configuration here that I was describing was studied years prior by both Thomson and Fermi, who both postulated a long time before the work I was just describing, that this configuration should lead to a rotation of the polarization this time. So what you have here is a linearly polarized wave that propagates and enters onto a rotating glass cylinder here. And what you get is that basically it exits with its polarization rotated azimuthally. And so this, in this case, is what's been coined by Fermi as polarization drag, because it appears that basically the polarization of the wave has been dragged by the medium. Since then, that's been explained in terms of circular birefringence as most optical activity. So in this case, you can show that the eigenmodes for propagation in this cylinder are circularly polarized. And that's the difference in wave index between those modes that gives you a polarization rotation. What's interesting is that the scaling of this effect is still the same as the Fresnel drag, that is group velocity minus 1 over phase velocity. And so this is basically a rotation of polarization that scales linearly with the rotation, the angular rotation of your medium, and that's proportional to that dragging coefficient. This was demonstrated very elegantly in the 1970s by Jones using the setup here. So you don't see it very well, but you have an incident beam here that propagates back and forth into a rotating glass rod here. And that's basically coming out here and being sent to a Wollaston prism to basically determine the rotation angle. And what you see here, so you have here like angle of rotation of polarization as a function of angular frequency of your rotating beam. And what you see here is that very nice linear fit that corresponds precisely to the prediction that was obtained by a player a couple of years prior. And that's basically what had been postulated long before by Thompson and Fairley. So if I just try to sum up what I've told you so far, that's basically well established in isotropic dielectrics. When you have a rotating medium and a wave, you have two different coupling mechanisms that correspond to coupling with different angular momentum components of your wave. One is with a coupling with the spin angular momentum, which is basically polarization. So what you get from that is that rotation introduces a shift between eigenmodes that are spin angular momentum. So that's basically a circularly polarized modes that are in yellow and blue here. And so you introduce a phase shift between those two modes. And what you get here is a rotation of the polarization that you obtain if you sum these two beams. And this is very much analog to what you would get from the rotation, for instance. The other coupling has to do with a coupling with the orbital angular momentum of the wave this time. So modes that carry orbital angular momentums are classically waves that have a screw wavefront like the ones in blue and yellow shown here. And so this time you're still introducing a phase shift, but now you're introducing a phase shift between these eigenmodes here. So what it does is that instead of having these two lobes that are symmetrical with respect to the vertical layer, they are not tilted by the same angle as what gets the polarization on the left. So these are two different aspects, two different coupling mechanisms between the rotation of a medium and the angular momentum of your wave, spin on one hand, orbital angular momentum on the other. Now, when we've said that, basically in isotropic dielectric, as I mentioned, both of these effects have scaling here. And if you take a normal dielectric, basically your group and phase index are of order one, whereas the rotation angular frequency is limited because of mechanical constraints. And so generally these effects are small and they are neglected. So now you might be asking, why am I saying all this if it's to be neglected? So the question we have to answer now is, why do we expect this particular quantity here to be larger in our plasmas? So the first thing that we can look at is basically this angular frequency. So as I was mentioning, in a solid dielectric, you can only spin it so fast until basically it's going to break down into mechanical stresses. In a plasma, on the other end, we can spin things much faster because we don't need any moving parts. We can do that electromagnetically. And so if you take, for instance, the 10 to 500 kilohertz that you may get into a tokamak, for instance, you get some 3 orders of magnitude increase compared to what's the maximal rotation frequency you could get in your solid dielectrics. And so that's already 3 orders of magnitude on the polarization rotation or the azimuthal drag that you can get. The second knob we can play on is the group velocity. So in that case, it's very well known that in plasmas you can have slow waves, for instance, an alpine wave that propagates at velocity much lower than the speed of light. And so in that case, you can also get an increase here on this particular contribution here of the group velocity. And so this is another way you can play another game you can play to increase those effects. Now, nothing is really new here. Basically, the idea of using a rapidly rotating dilute medium is something that's been used already to observe very large rotation of polarization in molecular superrotors. And conversely, the high group index is something that was precisely used to demonstrate the image rotation effect that was showing a couple of slides prior, using slow light in a rotating Ruby rod. So what's interesting in a plasma, though, is that we can, in principle, play with these two nodes at once. And so we can combine the effect of slow light with rapid rotation to get enhanced effects. The other thing that's fundamentally different to plasma is that all I've mentioned so far is basically in isotropic medium. Clearly, we're very well aware that in our plasmas, our susceptibility or permittivity are tensorial. And so basically what this means is that what I've described so far doesn't really apply to our plasmas. And so we need new theoretical tools and new ways to basically quantify these effects. All that says is that basically we should expect some effect, or we can expect reasonably some effect of motion and rotation in particular on plasma waves. So after this introduction on isotropic dielectrics, let me jump into what we've seen and learned in plasmas. So before discussing results, let me just tell you what's actually making this task not totally trivial. So if you want to study wave propagation in medium, the way you normally do that is that you obtain a wave equation from which you can get a dispersion relation. And a standard way to do that is to combine Maxwell equation with your constitutive relation. So to illustrate this, if you take your standard isotropic dielectric with the permittivity epsilon, you have the very simple the constitutive relation shown in that blue box here. And so from that, combining that with Maxwell, you show very rapidly that the eigenmodes are linearly polarized and that your wave index is the square root of the permittivity. Now, we're also very familiar with plasmas with the case where our susceptibility tensor is anisotropic. So in this case, you get the same sort of relation except they're not tensorial. And in this case, you also find from most plasma textbooks that you can still get analytical solutions, which are your classic plasma waves. Now, if we consider this motion, this medium to be moving, now we basically can get equivalent constitutive relation as seen from the lab frame by doing Lorentz transformation of the field from that frame in which the plasma is static, or the medium is static, which is my sigma prime here, to the lab frame, which is basically quantity, non-prime quantity here. So what you see when you do that is, as shown here, that you basically introduce what's known as a magnetoelectric coupling. What that means, something that's demonstrated by Röntgen. And so what you get in this case is that both B and D depend both on E and H. So this is a medium that's known as a bi-isotropic medium. And if on top of that, you basically consider a medium that is in a non-uniform motion, so that B here is a B of X, basically what you get is inhomogeneous bi-isotropic medium. And so now you need to combine those constitutive relations with Maxwell equation to obtain wave equations. And this is starting to be much less trivial, and you don't necessarily always find solution. Now, we can combine both difficulties and get now what's known as a tensorial magnetoelectric coupling. So what that means that now this dependence is tensorial and depends both on E and H. And so all the difficulties that we're already facing here are now just heightened here because we now have to deal with basically tensorial relations. In this case, you've got an inhomogeneous bi-isotropic media, which is the way you can describe a moving plasma as seen from the lab frame. So because this is quite challenging, we can't in general obtain wave equations. So what we've done is focus on specific configurations. So one particular configuration that we looked at extensively is what we called an aligned rotator. So what's an aligned rotator? It's basically just a simple cylinder of plasma that rotates in such a way that the axis of rotation is aligned with the magnetic field. That's what's shown here, magnetic field in green. Axis of rotation in red, and so basically I have a magnetized plasma that rotates with magnetized plasma column. Beyond being quite interesting for the analytical model I'll be deriving, the other appeal of this that basically captures reasonably well what you would get if you got a linear machine with a transverse or perpendicular electric field, or a perpendicular pressure gradient. So in this particular configuration, we looked more specifically at two wave configuration. One is a simple plane wave that propagates, again, aligned with the other two vectors. So now we have basically wave vector, magnetic field, and rotation axis that are all aligned. And the other configuration that we looked at is the case of an orbital angular momentum wave that propagates along the axis also. And in that case, basically, we have an azimuthal mode of plus or minus 2 in this case. So if you remember what I was describing for isotropic dielectrics, these two cases is basically the canonical example for, on the left, polarization rotation, and on the right, image rotation. So I'll be describing through this example now what we've learned in plasmas. So if we focus first on polarization, so the first thing I was mentioning when we talk about magnetized plasma, so all plasmas are not like isotropic. And what you get for polarization when you talk about plasma is that your plasma or magnetized plasma is basically optically active absent rotation. And this is basically your standard Faraday rotation that you get in magnetized plasma, which gives you polarization rotation that we use for a variety of applications, for instance, for diagnostics and astrophysics. One thing to keep in mind that I'll be using later is the high frequency scaling of Faraday rotation. So when your wave frequency is much higher than the plasma frequency and the cyclotron frequency, you can basically show that the rotation of polarization scales as the inverse of the wave frequency square or as the wavelength square. So that's something that's used in astrophysics, and I'll use it in a minute. So now the question we asked is what happens when basically you have now rotation. So from the discussion I was just giving you earlier, what we expect is a polarization drag contribution. So basically now an effect that would be entirely due to the motion or the rotation of your medium. So to verify this, we basically carried out the same derivation as the one that was done here, but starting this time from a gyrotropic medium, so from our magnetized plasma that is anisotropic in its rest frame. And what we found in this case is that indeed, if you have a rotating magnetized plasma, you can show that there are two contributions to your polarization rotation. One that comes from the magnetic field, which absent rotation reduces to normal Faraday rotation, and an additional contribution that comes from the rotation of your medium, and that one is basically entirely due to the rotation of your plasma. So the theory of this effect is something that we looked at in detail, so I won't be getting into these details now, but what it basically allowed us to do is also to look for places where we think we could possibly observe this effect. And one places that we found where we could possibly observe these effects is pulsars. So for those of you that may not be very familiar with pulsars, so pulsars are rapidly rotating neutron stars, so that's what's shown in gray here, that are surrounded by a co-rotating magnetosphere, which is shown in light blue here, and that emit beam-like radiation. And because of the highly polarized and localized source of pulsars, pulsar emission or pulsar signals, rather, are used to do a variety of things in astrophysics, and in particular, they are used routinely to infer interstellar galactic magnetic fields. So the way this works is that basically you assume that the rotational polarization that you observe on Earth comes entirely from Faraday rotation in the interstellar medium. So that's my screen here between point Q and point R. So that's basically an assumption you make. And if you do that, and you realize that basically for the typical gigahertz frequency at which those observations are made, you're way above the natural plasma frequency of your interstellar medium, which is not dense and very low field. So basically at gigahertz, you're way above the plasma frequency and the cyclotron frequency. You can use what I was mentioning earlier, which is that polarization rotation scaled as the wavelength square. And so you can basically fit the rotation of polarization that you measure on Earth as a lambda square function. Your fitting parameter being that Rm parameter, which is a direct measure of the magnetic field along the line of sight between Earth and the source of the pulsar, basically the pulsar location. And this is how basically in astrophysics, we routinely, or we astrophysicists and astrophysicists, routinely infer galactic magnetic fields. So question you might ask is why don't we basically consider what's happening between point P and point Q here, which is also what we asked ourselves when we saw that. And so the reason for that is that pulsar magnetospheres, are assumed to be filled with electron-positron plasma. And basically electron and positron interact symmetrically with RCP and LCP waves. And what it does to you is that basically, if you have a symmetrical electron-positron plasma, it doesn't yield to any Faraday rotation. That's basically what you can show very simplistically here by looking at the non-diagonal component of the susceptibility tensor. And you can show that basically this term is zero when you have basically an electron-positron plasma, because again of the symmetrical interaction of electron and positron with RCP and LCP waves. So this explains why there's no Faraday rotation between point P and point Q. But what basically was our question is, okay, so there's no Faraday rotation, but what about the mechanical contribution I was just describing? Because that one does not necessarily vanish if you have electron-positron plasma. So this is something we looked at in detail. I won't have too much time to get into details here, but basically we found that it does matter. And that basically what you find is that if you consider the normal gigahertz observation frequency that's being used to infer those galactic magnetic fields, at this frequency here, you have two different contributions that you measure on Earth. One is the Faraday rotation that I was describing, which is basically what is assumed to be the only source of polarization rotation. And the other here is the mechanical optical rotation or polarization drag. Those are basically synonymous. In this case, what makes things more problematic is that both of them have the same scaling. So you have no way of basically separating what comes from the effect of magnetic field in the interstellar medium from what comes to the rotation of the magnetosphere. What makes things worse is that when you estimate these parameters here and these two different contributions for typical parameters of pulsars, you find that basically this is not necessarily negligible. And so what that means is that you could basically wrongly attribute polarization rotation as measured on Earth to the interstellar magnetic field when basically it comes from the rotation of the magnetosphere. Interestingly, there might be a way to solve this problem. The solution possibly is to look at the lower frequency, because what we found is that at lower frequency, our contribution from rotation in the magnetosphere has a different frequency scaling, which is the one shown here. And although this difference is pretty small, it turns out that there's currently an ongoing development of high precision measurement capabilities for low frequency observations, which has nothing to do with what I'm describing here. It's basically used to do some pulsar timing arrays to study gravitational waves. But the precision of these basically instruments should give us a way to basically disambiguate these two different contributions. And if so, that could give us, on the one hand, a way to correct for possible error in the estimates of magnetic field, and on the other end, a way to determine the rotation direction of a pulsar, which is something that basically there are no other means to do at the moment. So that was the part on pulsars, which we're quite interested in finding, and we're actually still exploring collaboration with specialists. We're also quite interested in seeing how we could actually do that on Earth. And so basically in that case, since we don't have really access to the convenience of an electron-positron plasma in which Faraday rotation cancels, what you need to find is basically regimes where your Faraday rotation is going to be smaller than the mechanical contribution. If you really want to basically see this contribution, possibly use it. So what we found is that there is basically a frequency range, which is pretty low, which is below the ion cyclotron frequency, where basically the mechanical contribution is much larger than the Faraday rotation. So that's what you see on this figure here, where the solid line is the curve that accounts both for polarization rotation, that accounts for polarization rotation both from Faraday rotation and from the mechanical contribution, where the dashed dotted line here is only the Faraday rotation. And so what you see is that at low frequency, there is a range of frequency in between those two vertical lines here, where there is a significant contribution for the mechanical contribution. And so in this regime, basically what you're observing is what you're driving with rotation. What's interesting is that you can basically control the frequency range over which that announcement occurs by tweaking plasma parameters. And so what we found is that if you can push this to terahertz frequency, you could actually find with those rotating plasmas non-reciprocal properties that are very interesting for a number of applications. And so this is something that was interesting to find on the way along the way of these studies. When you look at what you need for that, you're starting to be at kilotesla field. So this is something that basically would have to be first observed if we want to have any chance in high energy density plasma experiments. So this is also something we're discussing with specialists, but that's still not really a tabletop experiment in the near future. So that was the effect on polarization. As I told you, we also looked at the effect on image rotation, that is the rotation of the structure of a wave. And so let me now tell you about what we found in plasma. So the first thing you need to know for that is that basically you need plasma waves that carry orbital angular momentum. So the good news that's been known now for over a decade that plasma, both magnetized and non-magnetized plasma, support waves carrying orbital angular momentum. And example of low frequency waves in magnetized plasma are with silicon, Alven, or triple piece gold waves. The way you can show that basically you can go back to the normal way you would derive a dispersion relation for these modes. But now you basically consider your perturbation as having an azimuthal dependence L theta here, which corresponds precisely to an orbital angular momentum content h bar L as shown there. So if you start with this perturbation rather than you basically azimutally homogeneous solution, what you get is that if you carry out standard wave analysis, you basically get eigenmodes now that have the form shown here, which is basically a Bessel function for your radial dependence, and the azimuthal dependence L theta, which is what's shown here, which basically captures the fact that you now have an OM carrying mode. We look at these modes more closely. So what you have here is the axial component of the perturbation of a Whistler-Dipon wave. So what you find is what's shown here. And so if you look at this more closely, you find that basically this azimuthal dependence L theta leads to a rotation of the transverse structure of your wave. So if you take, for instance, an L equal +1 mode, which is on the left, what you find is that you do have a rotation in the counterclockwise direction of the transverse structure that happens over one axial wavelength here. So you start with the blue on top, left, bottom, right, top here. And so your wave pattern is rotated by one rotation over one wavelength here, which is the outside wavelength. If you take the L equal -1 mode here, you basically have rotation in the opposite direction. So now it's blue at the bottom, bottom left, top right, bottom. So you've done the same stuff in the other direction. So this is basically a rotation of the transverse structure. This is not the polarization. This is really like the structure of your wave in the transverse plane. So what we can do now is sum those two modes. So basically we have a combination of modes with opposite orbital angular momentum. And what you get in this case is something very simple, which is an azimutally standing wave. So now there's no more rotation in this azimuthal direction. You just have a wave pattern that's basically static azimuthal. So once we just observe this by playing with those solutions, we can basically draw an analogy with what we know from spin angular momentum with polarization. So we all know that basically when you combine an RCP wave and an LCP wave with the same amplitude, you get a linearly polarized wave, which has zero spin. And so what I've just shown you and discussed here, that if you sum modes that now are orbital angular momentum modes with opposite indenness, what you get is a wave that has zero indenness, which means that it has zero orbital angular momentum. But this is absent rotation. So what we found also, and I will describe what I've described earlier, that when you have rotation, you basically now introduce a phase shift between your spin angular momentum modes that gives you polarization rotation. And what we had seen in isotropic dielectrics, so the same thing happened for orbital angular momentum modes in isotropic dielectric that give image rotation. So this is something we want to see whether that was also at play in plasma. So to do that, we basically carried out the same derivation as I was describing now. We still have the same perturbation, but we consider them now as perturbation around a rotating equilibrium. So if you do that, what you're going to find is that your axial wave vector beta here now is no longer only a function of the plasma parameters and your wave frequency, but also now of the rotation frequency capital omega and your azimuthal mode number L. So what it does, well, that's one result you find directly like this. What you can do with this is that now you can go back to summing modes. So if you sum modes with opposite L, basically, in the case absent rotation, what that tells you here is that your beta plus L and beta minus L are going to be the same. So if you sum modes that have opposite structure, you're basically going to get an azimutally standing wave. So there's basically no pattern rotation here. Now, if you do the same thing for a wave that is in a rotating plasma, so omega is different from zero, then from this relation, you find that basically the axial wave vectors are going to be different from the plus and minus L modes. And so you're going to get image rotation. That is, as you move along Z, which is going from left to right and top to bottom here, you do see a rotation of the wave pattern, which in this case comes from this difference in axial wave vector here. So this is a purely theoretical result. We figured that we could possibly observe it in experiments. So this is something that was done at UCLA in the large plasma device. So I'm not sure if you're familiar with the large plasma device, but that's basically a 20-meter long, 1-meter diameter machine that produces magnetized plasma with magnitude of the order of a few kilogauss. That is a pulse machine, so it's rep rate of 1 second, 1 hertz. And so you get plasmas like this that are highly reproducible that you can run for hours or days, and in which you can run experiments. So the idea of doing experiments on image rotation in LAPD actually builds on a previous experiment that was leading on LAPD, which was targeting control rotation in LAPD. So for that, we basically use bias electrodes that are positioned at one end of the machine here. And we impose different biases on these electrodes to drive rotation of the entire plasma column. And what we've shown in 2023 is that this, by the way, these are like basically experiments that are conducted as part of the Magnetius program in the US. So for which I get the chance to just go do experiments on LAPD. So what I was saying is that basically what we showed through the first round of experiments as part of the Magnetius program is that we can, by controlling the bias that we apply on this bias electrodes there, control rotation of the plasma column clockwise and counterclockwise, and control the amplitude of that rotation. So we basically have a way to create a rotating plasma column of somewhat controllable rotation. So what we did in this last set of experiments is to now include an antenna here that is a simple loop antenna, and that this sort of antenna is known to couple to the plasma generated in the machine in the form of kinetic Charpin waves, which are basically a variation of your classical Alpine wave that happens when your electron thermal temperature is larger than the Alpine velocity. And so what's interesting for us with this antenna is that it creates a wave pattern that is shown here. So what you have here is at 4 different instants through a wave cycle from left to right and top to bottom. So what you have in color code is the current, so the perpendicular current, that's your JZ in the machine, Z being the axis of the machine, and the arrows shows the transverse magnetic field. So what you see here is that you basically have 2 counter-current channels that flip direction halfway through the cycle. And what we found is that this is a very stable pattern. So what that means that we here have our azimutally standing wave that I was describing a couple of slides prior. So this is without rotation. What we wanted to see is how rotation is going to change this wave pattern. So what we've done is to consider three different biasing scenarios, which are three different roles here. On top, it's going to be clockwise rotation. In the middle, it's basically a baseline scenario where we don't do any rotation. And at the bottom, it is a counterclockwise rotation. So what we see here is data at time t1, which is before we bias. So basically, there's no rotation imposed on the plasma column. And so we find that the wave pattern is the same, which is basically consistent with what we wanted. What you have here in color code is still the current, the axial current of the wave perturbation. Now, compared to the previous slide, what you have now in arrows is no longer the transverse magnetic field. This time, it's the flow velocity as inferred from probes in the machine at the same time. So basically, at this point, we see that we have very little flow and three different structures that are the same. Now, if I plot data at time t2, which is what's shown here, there are a number of things to notice here. The first thing is that if you look at arrows only, you're going to see that you drive a clockwise rotation on top, counterclockwise rotation at the bottom, and no rotation in the middle, which is what we wanted. And if you look now at the color code of this plot, you basically see that the color map, the current channels have been rotated rightward on top, leftward on the bottom, and I haven't moved in the middle. And this is compared when you look on the left here, which are line outs around the circle that's like the dotted circle on the upper left. And what it shows is that basically an azimuthal shift of the current channel as you bias by set. So the azimuthal shift is by a few tenths of degrees as you bias going from left to right, depending on the direction of rotation of your column. So we're quite happy with that. We also wanted to see whether that fits the picture of the image rotation that I described earlier. So for that, even if we are here, clearly a magnetized plasma with all the complexity that comes with it, we basically can use the simple use. We can basically test whether that gives anything correct. Basically, we can test what gives us the simple formula I was showing at the beginning for transverse drag. So if you remember, D is the lateral shift. V is the velocity of your plasma in this case, so the transverse direction. And these are your work index and phase index of your wave. So if you take an alpine wave for the plasma parameters of LAPD, you're clearly in the regime where the alpine wave is much lower than the speed of light. And so that group index is very large. It's basically the square root of your perpendicular susceptibility. So what you get from that is that this formula can be roughly approximated by the formula shown here, which tells you that the lateral shift you expect should scale as a propagation length L, which in our case about 5 meters in LAPD. V being transverse velocity that you drive with the electrodes, which is a few kilometers per second in case of LAPD. And this alpine velocity that in this case is of the order of another kilometer per second in the LAPD condition. And so what you find from that is that you should get a few centimeters of lateral shift. And so once you have this, you can basically take the data here, take the flow from here, and reconstruct the solution. And what you get is what's shown on the right here, which shows you that basically you have indeed a rotation of the current channels that is qualitatively at least matching what we observed experimentally. And we find that we actually get even better match when we account for the fact that we don't actually have an isotropic medium and that our wave is not an alpine wave, it's a kinetic short alpine wave. So it has slightly different group velocity than what's shown here. So this was basically a quick walkthrough what we've learned in rotating plasmas to basically is the place where, or is the configuration where we're still capable of doing analytical work to get a better sense of what to expect in more complex configuration. That being said, we are well aware that basically plasma flows are really purely rotational, and that will also rarely have a simple normal incidence. So we basically want to just go from where we are now to models that will account for more complex load, more complex geometries. So this is something that we've been doing. And so now I'm just going to tell you in 3 slides what we're currently working on to get to the point where we can do that. And the direction that we're generally following for that is basically geometrical optics. So the first thing we did to just get to a more complex incidence and geometry is to consider actually a result that was missing in the literature, which is the analog of that transverse drag that we're showing on slide 3 for the case of an anisotropic medium, which is shown at the bottom here. So what you want to know, because your medium is now anisotropic, you have birefringence, so you've got multiple rays that are refracted. So what I wanted to know is for any incident direction, what are the group velocity direction and wave vector direction of the yellow and green rays here. So that's something that we derived in a very generic fashion for a plasma. And so now we can basically compute the drag for a moving plasma at arbitrary incidence. So just to illustrate what you can do with that, you can consider the simplest case shown here. So just to simplify things, you can take B to be out of the page. So what you get from that is that your moles in the rest frames are your normal O and X mole. And so what we get here is that we compute basically what's the angle between the group velocity and the wave vector as seen from the lab frame as a function of frequency. So the top, so those three different panels here are low frequency on top, middle frequency, intermediate frequency, sorry, in the middle, high frequency at the bottom. And so what we plot here is the angle between those two vectors as a function of frequency. The first thing you find is that absent motion, which is the blue arrows, the angle is 0, which is basically what you expect for your X wave, because the X wave has the wave vector and the group velocity that's aligned. But the second you start having some flow, that is a velocity in this case, that velocity makes it that this angle becomes finite. And in particular, you see that it's basically growing close to cutoffs and resonances, where this is interesting, but also probably pushing the limits of the models that we're using here. What we see with more confidence, the low frequency, you start seeing substantial angle here, even for a reasonable velocity of the plasma. And this is basically, again, the signature of the fact that the group velocity in this case is the alpha velocity. And this alpha velocity can be significantly smaller than the speed of light. And so you get a drag angle that can be some 10 of degrees for velocities that are way lower, like a beta that's 10 to minus 4, for instance. So this is interesting, but that's actually not the reason we started getting this very basic results. The result we got, these very basic results, that we realized that with the calculation that I just shown you, which is basically calculating the drag for uniform motion, we can now reconstruct what's the trajectory of a ray in a plasma that is a non-uniform motion. The way it works is basically we realize that you can integrate infinitesimal drag to reconstruct the trajectory along the ray. So that's what's illustrated here, where you have a medium that is layered with different velocities shown in red here. And so at each of these interfaces, you can calculate what's the transverse drag, which is what's dotted right here. And so basically you got your ray point by point or layer by layer. And if you take the infinitesimal limit of this, you get the blue curve here, which is basically the trajectory of your ray in an homogeneous field, velocity field, sorry. And for those of you that may be familiar with gradient index medium, this is the exact same approach, except that in this case, it's the velocity non-uniformity that appears as an inhomogeneity of the medium. So with that, we can start looking at some stuff that's probably much more interesting. So for the sake of simplicity, I'm still keeping the magnetic field out of the page, but we can very well just do things that are more complicated. And in that case, I basically have a wave vector that is incident on the rotating plasma column with a density profile, which is shown by the grayscale here. And so what you find here, so again, these are of the page, so I have two reflected modes that are the O and X mode. And so what you find here is solid line is the case with rotation, and dotted line is the case without rotation. So what you find is that both rays have different trajectory, which is what you would expect. The O mode first is unaffected by motion. This is something that we actually knew. And this is basically, it comes from the fact that the dispersion relation of your O mode is Lorentz invariant. So you can change to any reference. It doesn't change the fact that there's not going to be any sign of motion on the O mode. The X mode, on the other hand, is showing a separation of the ray with and without motion. So that what that means is that basically there is going to be a correction due to motion to the trajectory of your X mode in this configuration. And so this is something that could be important for energy deposition or for reflectometry. And these are two different directions that we'll be interested to discuss in the future. One last thing on this. So this is one way to reconstruct the trajectory in moving plasma, but it only gives you information on the trajectory. You don't get information on the polarization. And as I mentioned earlier, we're quite interested also at looking at the effect of motion and non-uniform motion in particular on polarization. So we explored in parallel to what I was just describing, a different approach, which basically is what's known as extended geometrical optics, which has recently been formalized by Ilya Dodin, but that builds on much older work from Little John and also what can be found in the book from Tracy Natoli. And so what you get from going to, by carrying basically extended geometrical optics, that you walk to next order in iconal approximation. What you get from that is that you basically capture what's the effect of correction and modification of the polarization along the ray which basically give you access to effects such as spin-orbit coupling, and in particular to correction trajectory that depend on the polarization. So what that means basically that if you've got two modes with different polarization in an homogeneous medium, they're not going to follow the same trajectory. And so this is something that has been, for instance, studied recently in work from Hongshin and Ilya Dolin, showing here that for electron cyclotron wave in classical tokamak geometry, you can get a deviation of your ray by some number of wavelengths when you capture for this sort of corrections. So this is basically the theory as developed by Ilya. What we tried ourselves is to basically work on it, to basically now use it to capture the effect of motion. So here, basically, the effects are due to inhomogeneity in your anisotropic medium. In our case, effects are due to the non-uniformity of the velocity. And we basically use Ilya's Dolin's formalism to work with a wave equation that captures the effect of motion. So we have very encouraging results for isotropic dielectrics. We are to the point that we think we're pretty close to basically having a way to just do that numerically, at least for moving anisotropic plasmas. And so we should be, at least that's the goal in the near future, to be in a position to do polarization ray tracing in moving anisotropic plasmas or magnetized plasmas. So that will give us access to studying the effects on the ray trajectory and the ray polarization of the movement in very realistic configuration, with the one limit that since we work in geometrical optics, we still have to deal with situation where inhomogeneities of the plasma and inhomogeneities or non-uniformity of the wave of the velocity field, are on length scales that are quite large compared to your wavelengths. So this is what I wanted to say on what we've done on basically what's the effect of motion on plasma waves. We also looked at the reciprocal question, which is basically not how motion is going to affect waves, but how waves can affect motion or plasma flows. We'll just have 3 slides to tell you a bit about this, and that maybe can lead to more discussions after. So the idea that we all know basically from plane wave that basically waves carry linear momentum, and that this linear momentum can be transferred in the form of radiation pressure. So this is basically how you're going to manipulate your atoms or particles, and this linear momentum transfer is also how we drive currents in plasmas. But as I described throughout this presentation, we also have waves that carry angular momentum in 2 different forms. One is the spin, which is the polarization, and the other one is the orbital angular momentum. So I've discussed that at length. So what's interesting to note here is that both of these degrees of freedom have been shown to couple to a solid medium in the form of torque, and basically you can drive rotation of a solid medium by using this angular momentum of the wave. So what it says that basically we can ask ourselves the question, can we use the angular momentum of the wave to drive plasma rotation? So why would we want to do that? Well, there are a number of applications where driving plasma rotation with waves would be highly attractive. One is magnetic confinement fusion. So canonical example is the rotating mirror, which is an old concept that's being revived through a number of ongoing efforts in the US especially. And so in that case, you can basically show that by driving rotation, you reduce axial losses and improve confinement in your mirror. And so this is something that's quite attractive to just try to do fusion in a mirror. And in that case, you certainly don't want to have electrodes, as I was mentioning earlier, because with hot plasma, there's no chance you're going to drive rotation with electrodes on the long run. So wave-driven rotation is definitely interesting there. Wave-driven rotation is also something that we considered to get confinement in toroidal geometry, where we showed that basically you could get confinement in toroidal geometry without the need for a toroidal magnetic field if you get wave-driven rotation. And the last application that we also looked at extensively is plasma separation. We would use rotation of the plasma to this time separate particles based on mass, which is also something that we worked on extensively at some point with that mission, for which wave rotation could be attractive. So basically, those are motivations to try to get a torque on the plasma from a wave carrying angular momentum. And so when we ask this question, what we basically want to do is to know how we can couple the angular momentum of the wave into our plasma. So again, for simplicity, we'll be considering a simple rotating plasma column. So what I mentioned earlier is that your wave has two different components. So you can basically imagine tapping into two different degrees of freedom for the angular momentum. And similarly, if you imagine that your plasma is E cross B rotating, you basically have two different degrees of freedom in which you can basically convert your angular momentum of the wave. One is the drift motion, and the other one is the cyclotron motion. Clearly, if you want to drive rotation, what you want to do is to just couple to the drift motion. And so this is something that we looked at theoretically. So we found that this could be done possibly through collisions, or basically in some collisional fashion. This is, for instance, the case of the alpine wave I was describing earlier, if you consider dissipation. And this is also something that we found that we could do resonantly through generalization of the cyclotron condition, which is basically corrections due to rotation that we call Brevard rotation. So basically, we have different approaches to attempt to couple angular momentum from a wave to the plasma to drive rotation. So this is what I want to say today. So basically, I hope I convince you that motion and plasma flows can have an effect on wave propagation. It might be something to look at. I'm not pretending this is going to be important all the time, apart from that, but there might be times that it could be important. So I guess the main point is for us to provide you with the tools that will make it possible to quantify these effects and make sure that they are negligible in the regime that we use theory that neglects it. So one effect that we've shown is an effect on the trajectory. So in that case, we're getting to the point that we could make estimates in realistic configuration, but basically, so far it suggests that this could be important for slow waves in particular, or close to cutoff and resonances. And this is something that might be important to look at for current drive, plasma heating, or diagnostics, reflectometry in particular. In the case of simple rotation and a wave carrying orbital angular momentum, this leads to image rotation, which is something that we actually observed on LAPD part in waves. For a rotation, or more generally, a non-uniform motion, there's also an effect on polarization, which we found to be possibly important in pulsars, but could be important in other parts of astrophysics, and also possibly in other environments. And as I was just mentioning, looking ahead, we certainly would like to basically quantify these effects in realistic configuration. So we already have a number of ideas, but I'm definitely very interested to hearing from you what you think could be interesting directions to study. Thank you.